Okay, good morning to all of you, and welcome to this morning's session. So Kedar twisted my arm and asked me to chair this. So today's first speaker is Professor Vijay Shenoy from IISc, and he's going to tell us about fermions and synthetic gauge potentials.
Okay, thank you, Ravi. This is not okay. So first of all, I'd like to thank Kedar and Subrata for inviting me. This will be the most unentangled talk of the meeting. So I assume that since I can barely spell the word entanglement, I assume that I was invited because these people are my good friends. Okay, so let me start by acknowledging people who have supported my research. Of course, the two funding agencies. And the key contributors of what I'm going to present today. The main part of the talk is the thesis of Jayanta Vyasanakari. He is now a faculty member at Tumkur University after having completed his PhD here. Sudeep Ghosh, who is in the audience. Adeep Agarwal, who is in the audience. And Umesh Yadav, who is on a train right now, is what I remember. Okay. All right. So overview, what I'm going to do in the next hour or so. In fact, Kedar, you had sent an email saying that we can add extra transparencies, which I have done, right? Okay, so I'll first I'll give you the background of this idea of what synthetic gauge fields and synthetic dimensions are, and I will raise some questions, and the remainder of the talk is answering those questions, and some of our work is, some of what I'm going to show is in these papers, and some of them are coming soon to be published. Okay, and some other people have also been contributing to this area, of course. And hopefully, at the end of the talk, you will see that these ideas that I'm presenting here will provide clues to some of the key questions of condensed matter physics, which is, for example, how do we produce superfluids with high transition temperature? And maybe even how do we make topological phases, and etc., with which we can do, for example, quantum computing. Okay, so this is the overview of what I'm going to be doing. So let me give you a little background. And for this, I'm very grateful to Rajdeep for very nicely giving you an overview of cold atoms. So I just request you to recall that. This talk is basically in the cold atom setting. So cold atoms, of course, promises lots of things. Okay, now that Senthil is here, I just wanted to make a couple of remarks. So I'm actually very honored to be giving this talk in the same thing as Chandrasekhar lecture as Senthil. I must say that Senthil is one of my first physics teachers. I got my first physics course, like a serious physics course from Senthil, and maybe in 2004, 2005, you may not remember. I did StatMech with you, right? Okay, so I'm very grateful for all the inspiration and so on. Unfortunately, you know, he likes colder weather better, so he moved to colder places. All right, okay, so one of the points that Rajdeep pointed out, the difficulty of using cold atoms as quantum simulators, is this idea that realizing fermionic strongly interacting states is hard because of this cooling problem, and he in fact suggested ways to come out of that. Then there is another issue in cold atoms, which is the trap, and as we saw in Ehud's talk and so on, it actually can be good, it can be bad. You know, one has to actually work on this. Then there is the overall picture of how do you do measurement and inference of a state that you get. This is also a very difficult and open, you know, we need creative ideas for doing this. And finally, if you want to, for example, simulate Hamiltonians with external magnetic fields, such as a quantum Hall state, for example, it's not simply possible for you to simply apply a magnetic field and couple to the momentum in some minimal gauge way, because the atoms are neutral. So what do you do? So here is where the idea of synthetic gauge field comes in. So the concept of synthetic gauge fields is the following. You create conditions either using light or some kind of time-varying potential in such a way that the effective Hamiltonian of the system mimics a system with an external gauge potential. This is the idea. This is what we call a synthetic. The atoms are neutral, so we want to endo them with some kind of charge, if you like. And that is obtained by doing, creating conditions where the effective Hamiltonian develops these gauge potentials. So several ideas are in the field right now. One of them is to use lasers and talk to the internal degrees of freedom. And the other is actually use like periodic driving of the system and generate these kind of gauge potentials. Okay? And one can generate both abelian and non-abelian gauge potentials, and there are several reviews in the market on this. Okay, so let me just first tell you that this is not science fiction, it has actually been realized. So these are very famous experiments by Ian Spielman, and what is shown here is generation of a U1 gauge potential in a Bose condensate which actually punches in vortices. Okay, and this is not by any rotation, it's by doing these gauge potentials. And some of the most recent experiments on this is actually realization of the Haldane model on a honeycomb lattice from the Tillman ETH group of Tillman oscillator. Okay, so this is one of the early experiments, and this is some of the more recent experiments. Okay, so I've just introduced this idea, and let me now give you just a very quick picture of how these gauge potentials can arise. So this, pedagogically, it's very nice to use this scheme, although it's not experimentally a good scheme. So let me just explain how these kind of gauge potentials can be generated. So what you have is you have an atom with, let's say, n plus 1 internal degrees of freedom. And then what you do is you use lasers and couple these states to the state 0. Okay? And then what you do, you can, if you just work out the math of this, you will find that the states organize themselves in this way. You will get a manifold of degenerate states, so these are called as dark states, and you get two other states, and you get m such states which is equal to n minus 1. Okay, this you can just show. And the important point is that this dark state manifold is actually spatially dependent. So what I mean by that is that because these lasers have this phase factor, which depends on position, this dark state manifold varies from place to place. So suppose I know the dark state manifold here. The dark state manifold here is related to it by some SUM matrix. Okay? So what happens, dark state manifold at position R is related to that at some other neighboring point by this kind of a matrix. And this U is, of course, e to the A dot R. You can arrange things in a way that this happens, where A is some elements of the Lie algebra of the SUM. Okay? So A then is actually a linear combination of the generators for each spatial direction, and these objects now are the gauge fields. Okay? Now, as the particle moves in this degenerate manifold, dark state manifold adiabatically, it actually picks up this connection, which was also alluded to in Joel's talk, for example, in momentum space. So you get this connection, and then the velocity operator, or the mechanical momentum, changes from the canonical momentum to this P minus A. So this is the scheme by which you can, for example, conceptualize how you get synthetic gauge potentials. This is not a good scheme for experiments because of this low-lying state, and anything that couples to that will immediately kill the gas. So there are other things that are used in experiment, but this is a very nice way to sort of visualize how things come up. Okay, so this is how gauge potentials are introduced. So now let me pose the questions that I want to ask. For this, I need to recall some more background. So let me start by discussing spin half fermions in 3 spatial dimensions in free vacuum. What do I mean by free vacuum here is that there is no gauge potential. So this is a well-known standard problem. And if you open Subir's book, at least in the first edition, it's clearly, I've not seen the second edition, you will see this phase diagram plotted. So what is this phase diagram about, or the flow diagram? You take 2 particles and ask, when can I form a bound state? So the interaction between the particles is described by this parameter V. And you see that in 3 spatial dimensions, you need a critical strength of attraction to form a bound state. And that is shown in this picture. If the critical strength is smaller than something, it is effectively as if there is no bound state, it's free fermions. If the critical state is larger than something, then there is some fixed point out there, which is like the deeply bound state. And then there is a resonant thing where you have a algebraically bound state, if you like. Okay, so this is the picture. And if you discuss this in physical language, this is some in terms of some interaction scale. If you discuss this in physical language, what happens is that the interaction is described by an S-wave scattering length. When the scattering length is negative, you don't have a bound state. And when the scattering length is positive, you get a bound state whose binding energy goes as 1 over scattering length square, and that is shown in this picture. Okay, so this is for 2 particles at 0 density, or phase diagram at 0 density. What happens if I have a finite density of fermions? So finite density is simply defined, the Kf defines the density here. And what we get is a BCS to BEC crossover. So let me just discuss this quickly. So if I have a small negative scattering length, which is somewhere here, where two particles do not have a bound state, the many particle system is still unstable to pairing. You get a BCS state with very large pairs and a chemical potential of the order of the Fermi energy of the system, as you can see here. And you get a TC which is exponentially small. Okay? On the other hand, if you go to the small positive scattering where there is a two-particle bound state, what happens is that the fermions pair up, they become a boson, and they Bose-condense. And here you get a TC which is of the order of the Fermi energy. And you have the chemical potential, which is now described by the binding energy or the energy of the boson, right? Because if you want to introduce a fermion, you can actually take two fermions and bind them together into a boson and stick it into the system, and that's why the chemical potential goes like this. And these bosons have a residual interaction between them, and that interaction is actually roughly described by again an S-wave scattering length, which is roughly twice this scattering length of the fermions. Okay, so this is the background. Okay, so now what I'm going to do is I'm going to introduce non-abelian gauge potentials for spin half fermions. And this is what happens. So I start with this. So typical experimental scenario, you will have, for this, there are 9 gauge potentials here because I'm discussing SU2, so there are 3 generators, and for each spatial dimension there is a gauge field, and I'm going to take them to be uniform, which is what is sort of envisaged in experiments. Okay, so you also get the Zeeman fields, which I will set aside for now, and just to be again close to what is done in experiments, I'm going to choose these gauge potentials to have this kind of diagonal form. What that means is that this gauge potential in the x direction has only an x component in the spin space, and the y direction has a y component in the spin space, and the z direction it has z component in spin space. So this gauge field configuration can now be described by a vector in the space lambda x, lambda y, lambda z, and this Hamiltonian now reduces to Hamiltonian with a generalized spin-orbit coupling. So uniform gauge potentials, non-abelian gauge potentials, is equivalent to spin-orbit coupling, generalized spin-orbit coupling like this. So this is the picture. Okay. All right, so what are the kind of gauge fields people are interested in? So, if you have gauge coupling just in one direction, so for example, when lambda x, lambda y is equal to 0 and lambda x is equal to lambda, this has already been realized experimentally in these groups. So we call them prolate gauge fields. If you have gauge coupling in all directions, there is a proposal for this. You see the point will lie here, and it's sort of a spherical gauge field. And what we call in condensed matter as usual Rashba spin-orbit coupling, which is spin-orbit coupling only for two-dimensional motion, is when you have lambda x, lambda y is given by this, and lambda z is equal to 0, and there are also several proposals for realizing this. Only these things have been realized experimentally. These have not yet been realized experimentally. Okay, to the best of my knowledge. Okay. All right, so let's just discuss one-particle states. So what happens in this generalized spin-orbit coupled system is that the spin of the particle, the spin-orbit coupling can be viewed as a momentum-dependent magnetic field. So the spin of the particle gets locked to its momentum, and you get two family of one-particle states labeled by their helicities, right? And this tells you whether the spin is parallel to the momentum or opposite to the momentum. And for the plus helicity state, for example, with the Rashba spin-orbit coupling, you see that you have a dispersion like this with a minimum at some finite value of momentum, and that value of momentum will of course be the magnitude of lambda. So this is the plus helicity state, and the minus helicity state has something like this. It does not have any minimum. Its minimum is at 0. So what you see is that the one particle ground state manifold is not a point. If I didn't have spin orbit coupling, then the one particle ground state manifold is just a point, which is the k equal to 0 state. Here you get a whole set of states at lowest energy. Okay? All right. Now I turn on interactions between fermions in the singlet channel. So this is what is done in cold atoms. So you can describe it by something like this. And let me not get into this. The main message of this set of equations is that even if you have S-wave interaction in the system, effectively you can even get P-wave interaction between these helical fermions, because you can have the S-wave can induce interactions between the same helicity states. Okay, so that's the message. Okay, good. So now I ask the question. I'm giving you a density of fermions, which is kf cubed, and a scattering length as. I'm giving you some vector in this configuration space. So this is spin orbit coupling. And I know what is the phase diagram when in free vacuum, which is when lambda equal to 0. So the question I'm asking is, what is the phase diagram here? So what is the what's happening in this question? So what happens to, for example, BCS BEC when you have this gauge? Okay, so here's how I'm going to organize the talk. So I will first discuss the ground state of the system. I will look at the two-particle physics, because these are dilute systems. Much of the physics can be understood by looking at few particles. Then I will look at the many-body ground state. Then I look at excitations, and then from there we will construct the overall phase diagram of this. Okay, hopefully I will have time to get into the other interesting stories. So I will discuss Feshbach resonance in a gauge field, and this is again related to what Rajdeep had introduced. And the reason for this is I would like to know under what conditions the phases that I get here will be realized. Then I may skip this. I will discuss Condo effect in this Rashba gauge fields. Quite interesting things happen there. Then I will show possibility of realizing new kinds of Hamiltonians. And I actually need synthetic dimensions because it has gone out of the dimensions of this. So I will actually discuss synthetic dimensions as well. Okay. All right, so let's start with this Rashba problem and discuss the two-particle ground state. Okay, so let's just start with the simplest case where I have gauge coupling in one direction. This is what we call a prolate case. And you see that the energetics of this is exactly same as what you had in free vacuum. You get a bound state for a negative, for a positive scattering length, or you don't have a bound state. So the first interesting result comes up when you have this Rashba gauge field where you have gauge coupling in two directions. Now you find that the scattering length required to form a bound state vanishes. What this means is that any attractive interaction in the system will produce a bound state for two particles. Right? That's the first interesting result. And you can see that for small negative scattering length, the binding energy is exponentially small. Okay, and because there is no, because we have broken certain symmetries explicitly, you will see that the wave function of the bound state has a singlet piece and a triplet piece and so on. Okay. All right, now you move on to the spherical gauge field, and now you again see that there is a bound state for any scattering length. And in fact, the bound state is so strong that even if it is negative, even if the scattering length is negative, the binding energy is quadratic in the scattering length, which means that it is an extremely strong bound state. So again, you have enhanced binding that shows up here. Okay, all right. Now you may say, okay, this has something to do with just some high symmetry gauge field. So what happens if you look at anywhere on the surface? So I'm characterizing the surface by these azimuthal and polar angles here on this surface. And you see that the critical scattering length required to form the bound state is negative on everywhere on the surface. So what this means is that the spin orbit coupling is actually acting to somehow enhance the attractive interaction between the fermions, and it promotes bound state formation. Okay? So that's the message of this. So how do we understand this? Okay, before we look at that, I just want to make a point about what happens if my scattering length were resonant. What I mean by that is that is the scattering length at which there is an incipient bound state in the free vacuum. And here, what happens at the infinite scattering length is that the binding energy becomes independent of the scattering length, of course, because it's infinite, and it's determined only by the spin orbit coupling. And the bound state wave function also is determined only by the spin orbit coupling, and its extent, the size of the bound state, is sort of lambda inverse of the spin orbit coupling. Okay, so how do you understand this enhanced binding? So I mentioned about the RG picture. So if you simply just do power counting, you will see that this Rashba interaction is relevant at both these fixed points. So you know something is going to happen. So what happens can be understood nicely by looking at the density of states, the infrared density of states. So what I'm plotting here is the density of states as a function of energy. And you see that for the prolate gauge field, there's gauge coupling in only one direction. You see that it is square root E, just like what you had for free particles in vacuum. And for the Rashba case, the density of states is a constant, and for the spherical case, the density of state goes as 1 over square root E. So the final message here is that the infrared density of states is determined by the codimension of the one particle ground state manifold. For example, if I have Rashba, then the ground state manifold is a ring, so the codimension is 2, and therefore I get the constant density of states in the infrared. If I have the spherical gauge field, the one particle ground state manifold is a sphere in momentum space of radius lambda, actually, and its codimension is 1, and you get 1 over square root E. And we can actually, just by observing this, you can reproduce all the results of the two-particle by making some model density of states, etc., and so on. So this is the physics of why you get enhanced binding in these systems. Okay, so having understood this, this two-particle physics, now let's move on and let's see what happens when I have many particles. So what I'm going to do is I'm going to traverse in this space in the following way. I'm at 0 temperature. I'm going to keep my interaction fixed, which is the scattering length fixed, and I'm going to increase lambda, and I'm going to see how the ground state evolves. Okay, before I do that, let me just ask what happens if I simply have non-interacting fermions. I don't have any interactions. Okay, so I start with some density, which is proportional to kf cubed. This is simply the definition of kf, actually. And then what I do is I just see what happens to the chemical potential when I increase lambda. So when lambda is much smaller than kf, you see that the chemical potential falls like this, 1 minus lambda square. And when lambda is much greater than kf, you see that the chemical potential falls, but it does something else. So you know something has to give in between, right? So what gives is actually the topology. So you see, you start with this is the Fermi surface. I've split the Fermi surface. Actually, there are two curves, there are two surfaces here, one red and one blue, and they correspond to different helicities, and they overlap here. So there are two Fermi surfaces here. As I increase lambda, the Fermi surface of the plus helicity states, the ones in blue, it sort of becomes like a, I think it's called as the apple of the torus, right? And the other is called as the lemon of the torus, this thing. That is the minus helicity states. And as I keep increasing lambda, you see that the minus helicity states are simply thrown out of the picture. And at a particular lambda, you see that there is a topology transition of the Fermi surface. This Fermi surface goes from a sphere to a torus, right? And it becomes like that. So in fact, we can see a movie of this here, if I can get it to work. Yeah, so I'm increasing lambda. It's undergoing transition. I'm bringing lambda back. I'll play that one more time. Right? So there's a change in the topology of the Fermi surface. Okay. So this is what is underlying in the non-interacting system. This is what's going on in the non-interacting system. And this topology transition, of course, takes place when lambda is of the order kf, because you know, that's the only scale. Right. Okay. All right. So now what I'm going to do is I'm going to keep the scattering length fixed and negative, which means my ground state, in the absence of any spin-orbit coupling, is a BCS superfluid. Okay. And then I'm going to ask the question, if I fix AS and increase lambda, what happens to the ground state? Okay, so let me just quickly show you these three plots. This plot has three pieces of information. The green line is the chemical potential of the non-interacting system, which I had discussed in my previous transparency. And this blue line is the energy of the two-particle bound state, or divided by a factor of 2 or something, right? This thing. And what I'm showing you here is the chemical potential obtained from mean field theory. And you see that at small lambda, it traces effectively the non-interacting chemical potential. And just about after the topology transition, lambda order 1, it switches and it starts to follow the chemical potential set by the two-particle problem. Right? So what this means is that there's some kind of crossover from a BCS-like state to a BEC-like state. Right? That's the message here. So the message is that, and we can of course look at the wave function of this Cooper pair and actually match it precisely with the wave function of the two-particle bound state and so on. Okay, the message is that this gauge field or spin-orbit coupling, when you increase it at a fixed attractive interaction, actually produces a BCS to a BEC crossover. So what kind of BEC is this? That's the question, right? So the crossover occurs in this lambda of that order of that lambda topology transition. And what is the nature of BC when lambda is much greater than lambda t? Okay. So now here's the message. The message is that for large lambda, the BEC is a condensate of a new kind of boson in the system, which is a bound state of these two fermions. And these bosons is what we call as rush bonds. Why do we call them as rush bonds? They're rush bonds because they are the bound state of two particles when the system has infinite scattering length. Right? So the properties of that bound state is completely determined only by the spin-orbit coupling and nothing else. Right? And so what you get is whatever scattering length you start off with, as you increase lambda, you will go to a condensate of rush bonds, irrespective of what the scattering length is. Okay, this is the message. So the gauge field induces a crossover from the BCS-like state, even for weak attractive interaction, to this Rashba BEC state. So this is the message. So what is the origin of Rashbans? Why do we get, where does the scattering length go? So if you simply look at, you can of course look at this in some RG language and so on, which I will not do here. If you simply look at it in some elementary way, if you look at the gap equation, for example, you see that this is the gap equation. And what happens when you send lambda to infinity is that the left-hand side goes to 0, right? And if you scale everything by lambda, the right-hand side is dimensionless, right? So what you get is whatever as you start off with, the left-hand side will go to 0, and therefore you will get the bound state corresponding to the infinite scattering length. And that is of course shown in all these pictures here. Okay? So sending lambda to infinity at fixed as is equivalent to keeping lambda fixed and sending as to infinity. That's the picture. Okay, so what's the summary? So I had asked this question, what is the phase here? And the answer is this. So you have a BC, in free vacuum you have a BCS to BEC crossover as you change scattering length. When you have lambda at a fixed scattering length, you start from a BCS state and cross over to this Rashba BEC state. And this Rashba BEC state here is the same state irrespective of where you start off from on that line. You will go into this. So this phase here, the state here is exactly the same state irrespective of what scattering length you start with. Okay, so that's the message. So now the question is, what is the phase diagram along the vertical axis, which is temperature? For example, what is the transition temperature of the Rashba BEC? So this is the question I will address. And for this, I have to ask, what are the excitations of the system? Okay, again, I will do it in the pedestrian way. I will first look at excitations of two particles, and then I will look at the excitations of the many particle system. Okay, so let's start with two particle excited states. So one way I can, if I have a bound state, one way I can excite it is to simply give it some momentum. So the particle will move, and if I take, for example, the second derivative with respect to the momentum, I will get the mass, inverse mass of the particle. Right? Okay, so that's what happens. So what I'm plotting here is that this is the energy of this bound state as a function of the center of mass momentum q, and this is made dimensionless by lambda. And of course, as expected, it is quadratic at small q, and from there we can actually find the mass of these particles. But we find something, actually this was discovered by Jayant. He found that at large center of mass momentum, the bound state actually vanishes. In fact, what happens is that at large center of mass momentum, even a positive scattering length in the system will not produce a bound state for you. So what was helping you to form a bound state at small center of mass momenta is doing exactly the opposite at large center of mass momenta. So how do we understand this? So this was also argued by Jayant. And so the idea is that the system has no Galilean invariance because you have put in this potential. And because you don't have Galilean invariance, when you go to the center of mass momentum, you see that the Hamiltonian changes to this. And in addition to this sort of change of velocity, you also get a Zeeman field associated with this center of mass momentum. And the Zeeman field actually splits the pair. Okay, so that's what happens here. Okay, so this is the story. So from here, we can of course extract the mass. I can extract the properties of Rashbans, etc. And so here is the plot of the mass as a function of lambda on this surface, if you, on this line, if you like. And you see that the mass is always between 2 and say 2.5 of the fermion mass. So this, I claim, is very important and very good because you will see in a few transparencies, because the TC of the Rashba BEC is going to be determined by this mass. Okay? All right. So let's discuss the excitations of the many particle system. So of course, there are Bogoliubov quasi-particles. And the dispersion of these quasi-particles inherit the change in the topology of the non-interacting system, and that's what is shown here, no surprise here. Okay, let's look at the collective excitations. There are phase modes and the amplitude mode, which is gapped. So here is the stiffness of the phase mode, and what I'm plotting here is the ratio of the stiffness of the phase mode divided by the stiffness in the system without a gauge field. And this quantity is proportional to the density of bosons or fermions in the system. And it is a result that comes from Leggett's theorem. It's independent of the scattering length. Okay, that it is sort of coming from Galilean symmetry. Okay, so what I'm showing you here is a plot of this as a function of lambda. And you see that there is a non-monotonic behavior here, right? So it is not set by the fermion density divided by the mass of the particles and so on. Okay, so this was actually observed by other people just before we put out, and this of course relates to the Galilean invariance. But our new result here is the following, that if you go to very large lambda, you actually have emergent Galilean invariance. And you get that the phase stiffness is actually determined by the density of Rashbons, which is actually density of fermion divided by 2, divided by the Rashbon mass. So you end up getting a new Galilean symmetry at large lambda. Okay, that's what happens. So what this means is that the Rashbons must be interacting with each other, because otherwise I wouldn't have had a finite phase stiffness. So what is the interaction between the Rashbons? Okay, so you can go and pull that out, and again you can show that the Rashbon effective theory is described by some Bogolubov theory of these Rashbons with some scattering, and the remarkable result is the following, that the Rashbon scattering length, right, is shown here. It is just inverse lambda. It does not depend on the scattering length between the fermions. So you start off with a system of fermions with some scattering length, you form these Rashbons, and eventually at large lambda you get these bosons, and they interact with each other by an interaction which is determined only by the strength of the gauge field and nothing else, right? And that's the result. And the scattering length is independent of the scattering length of the fermions. So in this sense, it's a nice state in which you start off with some constituents which were interacting with each other, and the excitations have interactions which are independent of the interactions between the constituents. So that's the picture. Okay, so we can understand where this comes from. It comes from the fact that the interaction between the Rashbons is actually determined by something like the Pauli exclusion principle, sort of keeping the bosons away because they are made of fermions, and the size of the wave function goes as lambda inverse. So that's why these Rashbons stay away from each other over a scale of lambda inverse. So that's the idea. Okay. All right, so let me now discuss the transition temperature and the full phase diagram. Okay, so it turns out that if you want to calculate this, you have to go beyond Gaussian effects and all. I will certainly not do that here. In the unlikely event of interest in this subject, we can take this up in the discussion session. Okay, so I start off by asking this question, and I showed you that this is the ground state, right? And here's the answer for the transition temperature at a positive scattering length. So what do I start from? I start from Tc, which is determined by twice the mass of the fermions, and then it smoothly goes over to the Tc determined by the mass of the Rashbons. No surprise. Okay, the first interesting result, which potentially has some use, hopefully, is that look at the Tc for a small negative scattering length. I start off with something exponentially small, it goes up, and then eventually it goes to this value, which is set by the Rashba. Right? So there is a strong enhancement of Tc in the system. Right? And here is what happens at resonance scattering length, and we can wrap this up by putting a little sheet on top of all these guys. Okay? All right, so this is the result for small negatives, for weak attractive interactions. You see, for example, if the scattering length is some 1 negative kf, 1 over kfs is 2, which is actually an extremely weak attractive interaction, where the Tc is something like 100th of Tf. You see, by increasing lambda to order 2, right, you see that the Tc can be enhanced to something like 0.15 Tf. Right? So this is the message that even for weakly attractive systems, you can actually enhance the Tc by engineering the spin orbit coupling. Okay, and of course the other message is that at large lambda, the Tc is independent of any scattering length. It is simply determined by the Rashbon mass. Okay, all right. So since I'm a little short of time, I will skip some of these things. So actually, in that intermediate lambda regime, there are some strong pseudo gap effects and so on. So let me not dwell on that. Okay. There have been experimental realizations of fermions in several groups that I'm showing here, but unfortunately none of these are the non-abelian versions of the system. It's just the abelian version. Okay, so we decided, since the experiments are doing this, we decided to quickly look at what happens here. Okay, so first thing we looked at, both motivated by the ongoing experiments and by the fact that we wanted to find systems where we can actually realize this Rashbon condensate. First thing is to see what kind of atoms can give you this kind of physics. So we studied this Feshbach resonance For that, we actually introduced the closed channel boson, and we did various modeling of various things. And then here is the result. The main message is the following: your Feshbach field at which the scattering length diverges, it actually shifts when you have this kind of gauge field, and we can actually predict the shift in some very quantitative way. And this is what our prediction was, and it is reasonably agreeing with the experimental measurements from NIST. Okay, and the second message that you learned here is that the Feshbach resonance actually has a width. Okay, this is for the cold atom experts. So there is a width of the resonance. And if you want to realize this rush bound state, the width has to be much greater than the spin orbit coupling scale square, right? Otherwise, you will not get this rush bound state. The reason for that is that the closed channel boson will actually strongly hybridize with the state and destroy the rush bound state. Okay, so that's the message here. Okay, and we also showed that in the experiments that are being ongoing, if you look at the translationally invariant system, not the system with the trap, the ground state actually has finite momentum pairing. It's something like a FFLO kind of state. Okay, so let me just skip this. It's just a result that we have. Okay, so now let me discuss what happens. So we are now trying to see what are all the things we can do with this gauge fields. So one of the things, this is Adeep's work, that we are sort of thinking about is what happens to Condo effect when you have this gauge field. Okay, so let me just give you, for the students at least, let me just give you a quick introduction of what is the Condo effect. It's just here. So what you have is you have a set of conduction fermions or free fermions in vacuum. And then you have some local state which can hybridize with this free fermion vacuum. And this local state, this so-called impurity, actually has interactions on it. So you have non-interacting fermions and one state in which there are interactions, U. And you can show that under appropriate conditions, the charge degree of freedom on this impurity state goes out, and the remaining degree of freedom is a spin on that, on that impurity. And that couples antiferromagnetically with this bath of fermions, and it forms a singlet. Okay? And that singlet has an energy scale called the Condo scale, given by this, where J is something like this. So this is all well-known stuff. Okay, so what we ask here is what happens if I have this spin-orbit coupling, which I introduced back, and what happens to this? Okay, so what is shown here is the moment on the D impurity side as a function of lambda and U. Okay, so you see first of all that to get Condo effect for small lambda, where lambda is less than the lambda required for the topology transition, you see that U comes down, and then U goes up. And the remarkably interesting thing is the following, that the moment in this regime of Condo effect is 2/3 the moment of the D electron that you would get otherwise. Okay? Again, I can discuss what is the physics of this maybe later. And the other point I want to emphasize is that the binding energy or the Condo energy scale is actually very large. So this was the Condo energy scale when lambda was 0. It is extremely small. It's exponentially small. And here it's actually order 0.1 EF, I think. Yeah. So the 2/3 moment, you just calculate the expectation value of the spin square on D. That moment. No. That will be 1. Okay, so I'll quickly tell you what the physics is. So what happens is when you have this kind of Rashba spin orbit coupling, if you hybridize an impurity, it immediately forms a very deep bound state. And then you can show that the effective weight of the D state in this bound state is 2/3. And that's at large lambda goes to some universal value of 2/3. The D moment. Total moment is 1. It's a singlet. Ground state is a singlet. Yeah, but the other interesting thing is that it enhances the TF. And okay, so actually the U takes over the role of hybridization and so on. Okay, I can discuss this maybe later. Yeah. Okay, all right. Let me also show you that there are many other possibilities that you can, of realizing new kinds of Hamiltonians in cold atoms using gauge fields and potentials. So let me illustrate this point. So imagine I take this, Rashba spin-orbit coupled system that I have, and I put on a potential. Now I write this potential, just like a quadratic trapping potential. Now I write this potential in momentum representation like this. Now if I work in a regime where this lambda is the largest scale, it is much greater than this, this frequency, then helicity is nearly a good quantum number. And what I can do is I can try to find the effective Hamiltonian of this wave function. And when you do that, you will find, you go through the standard exercise, you will find that this wave function senses a new gauge field, right? So gauge field can actually give rise to another gauge field when you couple it to a potential, right? And what can we do with this? Okay, here's an example. You take the spherical gauge field. So what happens here is that the spin is locked to the momentum in precisely the way I'm showing. It's parallel to the momentum like this, right? And as the particle moves around in momentum space, it will pick up a Berry phase. So that Berry phase is what gives rise to this effective thing that I'm talking about. So what happens when I have this spin-orbit coupling is that the potential, the kinetic energy of the particle goes like this: p square over 2 minus lambda by lambda times p. So this is minimum when p is lambda. So if I go to a large lambda, all my particles will have momentum magnitude p, and they will be moving on the momentum space on the sphere. But they also pick up this Berry phase. So it's actually a realization of a monopole in momentum space. Okay, so you can actually use this for doing various things and so on. Okay, so it opens a possibility to generate new and interesting Hamiltonians by designing. So it's also a designer Hamiltonian, if you like. Okay, and of course it doesn't depend on the statistics. Okay, so let me now introduce the idea of synthetic dimensions and conclude. This will be the last set of things that I'm going to tell you about. Okay, so so recently there have been a lot of interest in atoms which have SU-M symmetric interactions. So they have M hyperfine states, and there are SU-M symmetric interactions. I've given you examples of these guys. I've not given you the details of this, but these are the atoms and those are the M's. And several groups are actually experimentally working on this, and there are several theory works as well, which I have not cited here. Okay, so the idea of synthetic dimensions was actually put forth by these authors, Maciek Lewenstein's group from Barcelona. And so the idea is, you start with some optical potential, which is like a sinusoidal potential, and you have these SU-M atoms here. So an atom can be in this well, for example, and it can be in any one of these hyperfine states. And as it hops from one well to the other, the hyperfine state is preserved. Hopping is hyperfine, it commutes with the internal symmetry. Okay, now what I do is I introduce some light which couples these hyperfine states, right? So what do I get? I get some tower like this, and there is a hopping, effectively, between one hyperfine state and the other, which has a position-dependent phase. And this comes from the light. So now immediately you see that if I go through a placket like this, I start from the hyperfine state, this is m equal to 4, I start from the m equal to the second level and hop to the other and go up, come back, I pick up a phase, and that is this. Okay? And the remarkable thing here is that the interactions are SU-M symmetric, which means that the interactions are non-local along this direction. So everything interacts with everything else in that direction with with unchanged strength. So this will interact with this with the same strength that this interacting with that. Okay? So that is the, question?
It's like a strip, right?
It's like a strip in this direction. So if I remember right, holmium has 128 or something hyperfine. It can be big strip. Yeah. Okay, and so you can realize this thing. So the question is, what are the kind of phases you can get in this kind of systems? Okay, so this is what we have started working on with Sudeep and Umesh, and all that I'm going to show are their results. So there are some results already known in the system from this group when you do not have any of these phases and things like that. So that means you just have SU-M particles hopping without any other kind of fields. Sorry, I just meant to say this. So this is actually a Hofstadter model in the synthetic dimension, and with non-local interactions. That's the message here. Okay, so now what happens in this system when you do not have any of this, when there is no light, is that if you take M fermions with attractive interactions, they form what these authors call as a baryon, right? It's like some singlet object, like this. And this object hops from place to place with a hopping amplitude which is t power m by u power m minus 1. Right? That's what you get. Okay? Now the question we asked is, of course, what happens to this object when you have these phases and so on. And what Sudeep and Umesh have done is they have done exact diagonalization, and they characterize the states that you obtain by looking at some moment of inertia of this object, something in the spatial dimension, and this mean position in that direction. Okay, so here's the answer for m equal to 4. Sorry, I think I missed this. Okay, anyway, at least the picture is clear. This is for m equal to 4, and what I'm tuning here is omega, right? And what you see is that when omega was 0, you got this, this kind of tetramer object, and then it becomes something like this, which is what I call a dimer, right? So there is a dimer, and there are two dimers which form a bound state. So again, new kind of baryonic states. So since I have to use the word entanglement somewhere, right? So this is synthetically entangled. It changes to really entangled, right? This is entangled in the synthetic dimension, and this is entangled in the real dimension, right? So this is so you get a changeover, something like this. So we are, of course, there is a very rich phase diagram starting from some kind of general FFLO kind of state, which will evolve to a condensate of these objects. So we are kind of building that up as we are doing. Okay. Yeah, it's all negative U. It's all negative U, yes. If you had positive U, you would get anti-bound states of this kind above the. Okay, so let me summarize whatever I have told you, and I will still have about 10 minutes for discussion, right? So I showed you that with this Rashba kind of gauge potentials, there is a bound state for any scattering length. I discussed this Rashba spin orbit coupling, driven BCS to BC crossover. I showed you this Rashba BC, emergent Galilean invariance, and a system where you have interactions that are sort of independent of the interactions of the constituents. Then I showed you this phase diagram, and one of the promising things that comes out of this is the enhancement of TC, which is shown here. Then I showed you this very quickly. Showed you this finite momentum pairing. I discussed Feshbach resonance, what happens to that. I discussed the Condo effect, showed you ways of generating new kinds of Hamiltonians, and showed you this kind of changeover in the baryon structure in synthetic dimensions. So I'll stop here. Thank you.
Thank you very much. We have time for a few questions.
So I lost you a little bit in the first part when you are doing this Rashba spin orbit coupling. So did you take a 3D Rashba or two? So
no,
3D Rashba.
We have looked at all. We have looked at.
I mean, most of the results like Rashbone and all, it comes out only in a 3D Rashba spin orbit coupling.
No.
It's 2D
the
also.
Particles are moving in 3 spatial dimensions, but you get a Rashbone even if my spin orbit coupling is only in 2 directions.
Okay. So
other people have actually studied this in 2 spatial dimensions, and you get similar physics there. You of course get condensate, coastal skulls kind of things, but.
And another thing, so you said that this spherical gauge, which is like 3D Rashba spin orbit coupling, if I can call.
Yeah.
Have you studied that more and see what happens?
Almost all the results for which we have analytical results are for the spherical gauge field, because that's easy to handle analytically.
Because that Hamiltonian is very similar as Weil Hamiltonian, right?
Yes, in fact, right. It is.
So people have studied also Weil superconductor, and also all the results should hold there as well. In principle.
Yeah, but you see, in the Rashba limit, you are away from this Weil point where you're actually sampling only the dispersion, the bottom of the dispersion at large lambda, at a fixed density. Yeah. So the Weil physics does not show up here. In the Rashba condensate and all, the Weil physics is not.
Because your kinetic energy term is too strong. So in a Weil, you don't have that.
Spin orbit coupling term is too strong. Is very strong at large lambda.
No, in a Weil, you don't have that k square over m term, or if you
near the k equal to 0, that will not be there. You will just get this crossing.
Okay.
But at large, it will do this.
Okay. Yeah. Any further questions? Okay. So if not, let's thank Vijay once more.
Okay. Thank you.